And I guess we can just start off with this one right here. 1 over root x, 1 plus x dx. All right. If you can see that in the comments, let me know what you think is the best method to use here. This is one of my favorites. I don't know why. Lately, I've just been playing around with the roots. And it's just such a fun method. I have a lot of calc students right now that I'm meeting with, and a lot of the times they have problems like these that they like to go over. So typically, you know, it's all about just identifying the type of problem that we have here. Let me sort of zoom in here. Okay, so whenever we have these types of problems, the best thing to do is we want to work with the radical, okay? Because when we have the radical, we sort of want to almost get rid of it. So what we're going to go ahead and do is we're going to make u equal to root x. All right? And so now, because we want to get rid of the radical, we can go ahead and square both sides, and we get u squared is equal to x. You see that? Pretty simple, wouldn't you say? By the way, if you're here in the comments, please let me know if you guys can hear me. Hopefully the audio is pretty good. But anyway, here we are. We have u squared is equal to x. And so now what we can go ahead and do is to find our derivative of both sides. So we have 2u du is equal to dx. Not bad, right? Now that we have this, we're going to go ahead and plug some values in here into our integral. All right, so we have integral of 1 over, instead of root x, that is what our value of u is going to be. So we're going to go ahead and put a u, and then 1 plus, and then instead of x, look at this, x is equal to u squared. So we're going to go ahead and put u squared times, now our dx. Our dx was 2u du, so 2u du. And what's really nice about this is you're going to see that the u's cancel out. We have a u here, and the u on the top is going to cancel out. So what we're left with is 2 integral of 1 over 1 plus u squared du. And by now, I'm hoping that you guys could recognize this. Let me know in the comments if you guys recognize the integral 1 over 1 plus u squared, because this is a very important integral that we should know, especially if you're just starting off and taking calculus. Super important that we know this integral here. Let me know in the comments what you think this integral is going to be. Let me just go ahead and create a new page here. This is an integral of arctan. Right away, we should be able to identify that this is going to be arctan. So we're going to create this and make this 2 arctan of u, and then now our plus c. We found the integral. And now we go back. Don't forget that u was equal to root x. So this is going to be 2 arctan of root x plus c. There you go. That's my answer. Not too bad, huh? By the way, if you guys can't hear this, I'm just going to go ahead and put audio okay. Let me know in the comments if you guys can hear me. Can y'all hear me? Let me know in the comments if you can hear me. I'm hoping that you can. Yes or no? Just someone please comment. Let me know if you guys can hear me. I'm going to assume that you can. Okay, cool. Y'all can hear me. Thank you very much. Thank you, Victor. You're the best. All right, guys, that was a simple integral. And again, dealing with those radicals, always fun to do. Okay, so let's go ahead and do another integral here. And as I'm writing this, I'd love to know, where are y'all tuning in from? Where in the world are you holding your phone, watching some math nerd doing integrals? All right, here comes the next one. Ooh, this one's fun. Okay, I let that little zoom in there. Got that focus. All right, let me know in the comments what you think we should do here. I feel like I have an idea. Let me go ahead and take a sip of some coffee here. Ah, man, nothing like a fresh brewed cup of coffee in the afternoon, huh? Okay, immediately when you see this integral, to me at least, I see a algebraic function. I have an x, and then I have a trig function. So I'm thinking, and I'm hoping this is going to be the case, that we're going to use integration by parts. So remember, integration by parts is the ultraviolet voodoo. So uv minus integral v du. So we have to establish what the u is going to be and what the v is going to be. Typically, the u is the one that you can easily take the derivative of, and when you take the derivative, it makes things a lot easier. So in this case, what I'm seeing is that since u is equal to x, then I'm going to go ahead and make my du equal to dx. I think that's looking pretty good so far. And our dv has to be the remaining term, so that's the tan squared dx. Tan squared x dx. Now, we just have to sort of integrate this, okay? Now, before we do this, let's just go ahead and think about some trig functions that we should know. I know that 1 plus tan squared x is equal to secant squared x. So if I move the 1 to the other side, that tells us that tan squared x is equal to secant squared x minus 1. So we can go ahead and rewrite our dv as secant squared x minus 1. You're going to see why I did that. Okay, so dv is equal to secant squared x minus 1 dx. Because guess what? Now when we try to find v, when we take the integral of this, the integral of secant squared x is just tan. So we have tan x minus x. I think that's much easier. Okay, so now we're going to go ahead and implement the integration by parts, the ultraviolet voodoo. All right, so we have uv, so our x times this entire value. So we have x tan x minus integral of v du. So that's tan x minus x dx, because that's our du. Our du is dx. Pretty good, I would say. All right, so this is just going to be left alone because we don't have to integrate that. So I can just maybe do x tan x minus x squared minus, let's go ahead and integrate this. Now, again, the integral of tan is one that's highly, highly important to know. And I believe that's going to be negative natural log of cosine of x. Okay? And then don't forget, I'm distributing this negative sign to both of these values. So this is just going to become a positive. And then I'm also going to distribute this negative sign to this one. And when I integrate that, that just becomes positive x squared over 2 plus c, baby. Okay, let's just simplify this a little bit by making this a plus. So our answer is x tan x minus x squared minus, or plus, I'm sorry, natural log of cosine of x plus x squared over 2 plus c. And I realized that you can also combine the negative x squared and the x squared over 2. And that'll just become x tan x minus x squared over 2 plus natural log of cosine x plus c. There you go. That is our answer, guys. Give me a thumbs up if you like that problem. That was really nice, I would say. Cool. All right, let's try another one. This next one I particularly like just because, you know, you play around with some substitution and rewrite some stuff and then use the original value that we chose for u when we substitute it into our integral. All right, here we go. Let that zoom in. Okay, guys, let me know in the comments what you would do here. What exactly would you like to do? And if you have nothing, if you have no idea what we have to do, go ahead and give me a follow. Why not? Do something. Double tap that screen, follow, subscribe, whatever you want to do. I know I mentioned in the very beginning that we had roots and we're going to kind of play around with that. And we sort of are. Ooh, someone said integration by parts. Okay, you know what? I actually don't know if that's going to work, but shoot, why not? Why not try it? Okay? One of the things about integration, and I think that's why I truly enjoy these problems, is because it's all about just, you know, examining these methods. Now, I don't know if integration by parts is going to work. However, we're just going to take a gamble with it, okay? We're going to go to war together with this. All right, so I'm going to use integration by parts. And if that's the case, I want to make, God, I think I want to make this my u. Okay? We want to make this our u, and if we're going to use integration by parts, that's going to be our dv. Only because I don't know how to take the integral of that. I can take the derivative. So now let's go ahead. We make our u equal to root 2 minus x cubed. And at this point, when you're doing integrations, especially something like this, we should be pretty proficient in taking these derivatives quickly. So I believe this is going to be negative 3x squared over 2 root 2 minus x cubed dx. Let's see if that's even going to help us. Okay, that was our du. Now we go back to our dv, which is x cubed dx. And so our v is just the integral of this, which is going to be x to the 6th over 6. What are we thinking? Integration by parts might have helped? I don't know. I'm going to say no, but let's try this. Let's just try this one more time and see if it works. Now you have uv, so x cubed over 6 root 2 minus x cubed minus v du. So here's our v, x to the 6 over 6 times du is this entire thing. So this is like negative 3x squared over 2 root 2 minus x cubed dx. Ooh, you see that? And again, we were just attempting this. We didn't know if this was going to work, but it's all about just trying methods. And looking at this, I don't know, it's looking more difficult than it already was. So I'm going to say, you know what, integration by parts, we don't want to go that route yet, so it didn't work, but that's okay. All right? The whole point of this live is just to sort of practice. That's what happens, okay? This is where I make the mistakes. I try things out so that later on when you go out into the field, when you're taking this, when you're taking a test with your teacher, you already know the proper method to use. Okay, so let's use U-substitution. That's one of the basic ones that we typically have. So we'll make, let's go ahead and make u our inside value. And then so when we find our du, this becomes negative 3x squared dx. Okay, not bad. I like it. Picasso. Let's go ahead and divide the negative 3x squared to the other side so that we have du over negative 3x squared is equal to dx. I think this is good because now what we have is we're going to have integral of x to the 5th root 2 minus x cubed, which is just going to be u, times dx, which is this entire thing, du over negative 3x squared. And this is okay, because check this out. The negative 3 is in the, oops, didn't mean to use my eraser. There we go. Okay, the negative 3 is in the denominator, so we're definitely going to pull that out. And notice that we have an x to the 5th, and then we have an x squared. So this is like saying x to the 5th over x squared if we were to combine these things. And if you know properties of exponents, this is x cubed. So then now what we have is we have negative 1/3 root x cubed root u du. And this is okay because we still have obviously a bunch of u's and some x's. Not a bunch of u's, just one u, and then we have 3 x's. But don't forget, we know what this is, right? So let's go ahead and move the x cubed to the other side to make it u plus x cubed is equal to 2, and then move the u to the other side. Okay, just kind of showing the basic algebra there. Now we know x cubed is equal to 2 minus u. We can go ahead and plug that in here. Okay, so we have negative 1/3 integral. And then what did we say this was? 2 minus u. All right, let's go ahead and plug it in. So we have 2 minus u times, and I'm already anticipating this. I'm playing defense, so I'm just going to go ahead and rewrite this as u to the 1/2. This is just my root u. Because now we're going to go ahead and simplify, or not simplify, but distribute the u to the power of 1/2 to both of these. And now we have 2u to the 1/2 minus u to the 3/2. Practice those fractions if you don't see how I got that. Nice. And now we can just implement the power rule. So we have negative 1/3. And then this is going to become 2u to the power of 3/2. I added 1 to the power divided by 3/2 minus u to the 5/2 divided by 5/2. And then obviously we're going to have our plus c. Let's go ahead and continue simplifying. So we have negative 1/3. And this is going to become 4u to the 3/2 over 3 minus 2u to the 5/2 over 5. This is what I keep saying, to practice your fractions, okay? 2 minus u cubed, I forgot it. Oh, I did not. So remember, we were here, x cubed. We said x cubed is equal to 2 minus u. x cubed is equal to just 2 minus u. That entire thing is equal to 2 minus u. So this right here is your x cubed. So when I substituted that, I didn't need a cube. All good, all good. This is why we're doing this together, right? We're looking at this, we're talking math, and sometimes I make mistakes too. So please, if you see something, let me know. Anyway, so now our final step is we're going to go ahead and distribute this negative 1/3 to every single term, both of these terms, and at the same time, I'm going to go ahead and rewrite my u. Remember, u was equal to 2 minus x cubed. So that's what I'm going to go ahead and plug in. So now what we have is negative 4 over 9, 2 minus x cubed to the power of 3/2 minus 2 over 15, 2 minus x cubed to the power of 5/2, and then plus c. And if you have a crazy calc teacher, they will not accept this answer because they're going to want you to simplify the radicals, but we're not worried about that today. All right? But just sort of keep that in mind. All right, math nerds. This was a really, really fun one. Let's go on to the next one. And let's not worry about this like U-substitution stuff. Let's not worry about that. Let's go ahead and rewrite another problem that I think should be sort of fun. Okay, let's go ahead and do this one right here. And by the way, just so you know, I do have these replays that are going to go on YouTube. So if you subscribe to my YouTube channel, you can rewatch these at your own speed and practice these on your own time. Okay, actually, let's change this up. I don't want to do this one yet. Let's actually do x squared plus 5x plus 6 dx. All right, gang. As you're seeing this, let me know what method you think we should use. And please don't say integration by parts because I don't even know what I would do with myself. Taking a sip of coffee. Got my coffee right here, gang. I don't know if you can see it. But anyway, looking at this, let me know what you think we should do. I have the integral of 1 over x squared plus 5x plus 6. Integration by parts. What did I just say? Do not give me integration by parts. I can't deal with that right now. It might work, but I don't know. Partial fractions. There we go. Someone said factor. And I agree. So someone said factor, and then before that, someone said partial fractions, and I'm seeing partial fractions again. Absolutely. So if you have a quadratic like this, all right, let's go with those partial fractions, all right? So we're going to go ahead and first factor this. If we can, that'd be great. If we cannot, then we'll have to deal with that in another way. So this, it looks like it factors out to x plus 3 times x plus 2. Let me know if I got that incorrect in the comments. If not, great. So what happens whenever we have a problem like this is we want to rewrite this, okay? I'm just going to focus on the actual function, not the integral part. Remember, this 1 over x plus 3 times x plus 2 has to equal to the sum of two separate rational expressions. Now, the only thing about this is that we don't know what a and b is, and that's what we're going to find out. That's the whole point of partial fraction decomposition. So if you were to think about this and get common denominators, we would get that the numerators, a times x plus 2 plus b times x plus 3, has to equal to the numerator on this side. So this has to equal to 1. All right, we're going to go ahead and find the values of a and b, and the way we're going to do that in this case is really easy for us, is the cover-up method. And the way it works is we want to find a value that we can plug into one of the parentheses to cancel it out. What I mean by that is, look what happens when x is equal to negative 2. I get 1 equals a times negative 2 plus 2 plus b, negative 2 plus 3. Ignore the colors there. And so now what we have, 1 equals, check this out, this cancels out. And so what we have here is we just have negative 2 plus 3 is just 1, so b. So 1 is equal to b. This is perfect. Okay, let me go ahead and move this up so the comments do not cover up the problem. Let's try it the other way. Now let's make x is equal to negative 3. So we have x equals negative 3, and we have 1 equals a times negative 3 plus 2 plus b times negative 3 plus 3. What do you know? this cancels out on this side. And so now what we have is negative 3 plus 2, which is negative 1. So 1 is equal to negative a, meaning that a is equal to negative 1. So back to our problem. Remember what I said, 1 over x plus 3 times x plus 2, we said should equal to a sum of these two rational expressions. And we ended up finding the value of a and b. A was equal to negative 1, so this is negative 1 over x plus 3, plus b was equal to 1, so 1 over x plus 2. Aha! And we were taking the integral of this whole thing, so I can just say, okay, I'm taking the integral of this, and this is another opportunity where you have to remember what these values are. And this is going to be a natural log type problem. Okay? So this is going to become negative natural log of x plus 3 plus natural log of x plus 2 plus c. Perfect example of partial fraction decomposition. Okay? As I mentioned, I do post these lives on my YouTube, so if you feel like I'm going too fast, so if you want to take your time or see other lives that I've done before, go to my YouTube channel and you can find them there. Awesome. Okay, all right, guys, let's go ahead and do another one. And so we just did one where we had partial fractions, where we were very fortunate enough to have something that we can factor out. And so now let's go ahead and try a different one. And what happens when you have this? Whoops. 1 over 1 over x squared plus 2x plus 5 dx. All right, gang. What do we think? I'm going to take a sip of my coffee, but you go ahead and let me know in the comments what method we have to use. In the meantime, double tap the screen. Follow me here. Subscribe to my YouTube channel. So follow me on Instagram if you like. But let's see. What do you guys think? Let me know in the comments what we should do. Someone's saying complete the square. I like that. So this is very similar, somewhat similar to the previous problem. And every time we have a quadratic on the bottom, we should think, okay, can I factor it? You should ask yourself that. Can I factor this out? Okay? And in this case, we cannot. So we have to use something else. Now, someone said complete the square, but I just read, someone said U-sub. Let's try U-sub. Let's just see what would happen. Okay? If we did U-substitution, I'm assuming we will make the entire denominator RU, and then we get du is equal to 2x plus 2 dx. If you notice, there's no 2x plus 2 somewhere to cancel out, so it's going to be a little more difficult to do that, okay? All right, so in this case, and I will do a problem right after this where U-substitution will work, okay? But if you have a problem like this, I would suggest you can factor. U-substitution, maybe not the best method, but that's okay because we always want to try it. So let's go ahead and start about completing the square. Okay? Completing the square is really fun, and I hate this method so much. With everything in my body, I hate completing the square, but it's so helpful, and it's so essential in any calculus or upper level math class. So how do we complete the square? If y'all remember from an algebra class, we're going to go to the bottom, and we're going to say, okay, remember, we take our b value, which in this case is 2. We're going to divide it by 2 and square it. So 2 divided by 2 is 1. Squared is just 1. So that's what we're introducing here. But don't forget, completing the square tells you that because you introduced a 1 here, we need to also subtract it. And what does this become? We have 1 over. Now, the reason why we're completing the square is because this right here, x squared plus 2x plus 1, can now turn into x plus 1 squared. Practice that on your own. Or, if you want to, please, 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 watch the replays when I post it on YouTube and practice that. Okay, so x squared plus 2x plus 1 becomes x plus 1 squared. I saw someone put x plus 0.5 squared. Be very careful with that. And now we have 5 minus 1. That's going to be a plus 4. Guys, this right here, this is why we're doing this. Because now we have an x plus 1 squared plus 4. This is an arctan type problem. Let me show you. If we make u equal to x plus 1, this is where we use that u substitution someone mentioned. Du is going to equal to dx. And then our a squared is equal to 4, meaning that a is equal to 2. This is why I'm doing this. Let's go ahead and create some space here so y'all can see it. This is going to become 1 over u squared, because that was our u value, plus 2 squared times du. Okay, this is a very general form of an arctan, okay? And this becomes 1 over 2 arctan of u over 2 plus c. If y'all don't remember the arctan, it goes like this. Whenever you have 1 over u squared plus a squared du, the integral of this is 1 over a arctan of u over a plus c. Okay, that's where I'm getting that from. So going back to this problem, we have 1/2 arctan of u over 2 plus c. What was our u value? Our u value was x plus 1. So now we have 1/2 arctan of x plus 1 over 2 and then plus c. Let's go. Easy. By the way, guys, I try to do this once a week here on TikTok around this time. I think Wednesday is going to work. And then I do it on Tuesdays on Instagram. So if you want to follow me there, watch those lives on Tuesdays. And then I'm here Wednesdays and I post them on YouTube for replays. And then on Fridays, I try to do a live on YouTube just explaining other concepts. I think this week I'll probably do like graphing rational functions or something. All right. Let's go to this next one. I feel like we're seeing, a variety of different integrals. And honestly, if you're confused with all these, it's okay. This is all about practice. I've been doing this for so long, I can kind of identify some of the problems and some of like the methods that we can use right away. But I highly encourage you to do as many methods as you can every single day. This is how you get better. In my opinion, integrals are like, just like algebra, the foundation of calculus. Not really the foundation of calculus, but you guys get the idea. Okay, let's try this one. All right, chat. Let me know what you think we can do in the comments here. This is one of my favorites. I call this the pun integral. Someone say U-sub, polynomial division. Oh, I don't have an integral like that, but I'll definitely try to come up with one right now. Maybe the next one will be a polynomial division. But polynomial division typically will happen if the degree of the top is larger than the bottom. Okay, and in this case, the degree on the bottom, not so much. It's higher here, so we're probably not going to do polynomial division. Someone said U-sub, and I completely agree that U-sub is gonna be the best method here. Why? Because we have a 2x plus 3. It's kind of looking good. It looks like a U-sub would work, but check what happens when we have U-sub. So u is equal to x squared plus 6x plus 10. du is equal to 2x plus 6 dx. So if I move the 2x plus 6 to the other side, 2x plus 6 is equal to dx. Look what happens, okay? So we have integral of 2x plus 3 over u times du over 2x plus 6. So that doesn't necessarily cancel out. Gosh, we're so tempted to just say, okay, the 2x goes away. Whoops. We're tempted to say the 2x goes away and then the 3 over 6 just becomes a 1/2. Can't happen, okay? And then someone said, my bad, completing the square is the best method. It's actually a little bit of both, okay? It's going to be u-sub and it's going to be completing the square. So when you have a problem like this, all right, oh, someone's coming in here. Yes, someone already brought this and talked about the method that we're going to use. So again, we are going to use completing the square, but we're also going to use u-sub. So just look at what we did, all right? Just by doing the u-substitution, we kind of know that we want 2x plus 6 on the top. So this is why I call this the pun integral, because we're preparing for u-substitution in the numerator. Pun. I don't know why I use it like that. But anyway, the reason why we're doing this, okay, is because on the top, we're going to go ahead and add a 3 and subtract the 3 at the same time. Because 3 minus 3 is 0, doesn't really affect it. But when you start combining stuff, look what happens. If we combine the 2x plus 3, these terms here, we get 2x plus 6 minus 3, which was the minus 3 on the outside, over x squared plus 6x plus 10 dx. And the reason why we're doing this, okay, is because we're going to separate this into two different integrals. We're going to do 2x plus 6 over x squared plus 6x plus 10 dx minus integral of 3 over x squared plus 6x plus 10 dx. Y'all, check this out. This is going to be a U-substitution type problem because we already kind of did the U-substitution and we got the 2x plus 6. And this is going to be a partial fraction. Not a partial fraction, actually. It's going to be a completing the square type problem. Check this out. Okay, we already know that this is our U. I'm just going to quickly do it. U is equal to x squared plus 6x plus 10 du. Sorry for the blurriness. I don't know why my camera is not catching that. But anyway, du is equal to 2x plus 6. So du over 2x plus 6 is equal to dx. And now, this is just for this first integral. We'll focus on the second one after. We're going to have integral of 2x plus 6 over u times du over 2x plus 6. Look at that. Cancels out, baby. So now we have integral of 1 over u du. And this is just natural log of u. And then I'll talk about the plus c after. I'll add it at the end because we still have to deal with this one. So u was equal to the x squared plus 6x plus 10, this one. So we're just going to go ahead and plug that in. Natural log of x squared plus 6x plus 10. That's the first one. Let's go back to this one. Okay? Remember, we have to use completing the square here because this can't factor out. So what I'm going to do is I'm going to take out a 3 on the outside. And now we have 1 over completing the square, x squared plus 6x. Remember, take the 6 divided by 2 and then square it. 6 divided by 2 is 3 squared. That's 9. So we have plus 9. And then we have plus 10. And then we have to subtract a 9. Because it's all about keeping things even. Whoops. Here we go, y'all. Now this becomes minus 3 integral of 1 over, and remember, this can factor out. The x squared plus 6x plus 9 becomes x plus 3 squared, plus 10 minus 9 is 1 dx. And if you recall, we did this in the previous problem. This is an arctan form, where u is equal to x plus 3, du is equal to dx. A squared is equal to 1, so a is equal to 1. Okay. I'm not going to do the U substitution part because, again, this is something that we should sort of know. And then at the end, this becomes, let me go ahead and move this, minus 3 not natural log, minus 3 tan inverse of u over a. And so at the end, this becomes minus 3 tan inverse of u, which is x plus 3, over 1. I'm just going to put it there, plus c. Guys, this is my integral. That's what happens when you can't use partial fractions, when you couldn't use U substitution. We had to rewrite and prepare for U substitution in the numerator. I call that the pun integral. Extremely fun. And if you're taking Calc BC, Calc 2, some people call it, this is probably what you've seen before. Calc AB, maybe not so much, but still, this is extremely fun. Okay, someone said, can you do the integral of cotangent squared? Bro, why you gotta throw it at me? Any idea, guys? Any idea what we can do here? Okay, I actually don't know if this is correct. This is why we're doing these things. And typically, every time we have this integration technique practice alive, someone brings a problem. And if we can't solve it, maybe we can't solve it. I think it's quite simple, too. I think, if I recall, I'm hoping this is correct. I know, and I'm basically going to expose myself. I'm just going to show you. I'm going to show you how I get this. can we say that 1... Oh my, I'm sorry for the blurriness, guys. I don't know what's going on. But anyway, can we say that 1 plus cotangent squared x is equal to cosecant squared x? Or maybe is it the other way around? Is this, I think this is a proper, rule. I'm almost certain this is a proper rule. Okay, because now what I'm going to do is I'm just going to bring the 1 to the other side so that we get cotan squared x is equal to cosecant squared x minus 1. And then now I have, instead of integral of cotan squared, I just have integral of cosecant squared x minus 1 dx. And I believe this is, if I separate this just to show all the work, I'm just going to separate this into two different integrals. I believe the integral of secant squared is just negative cotangent. And then this is just the integral of x plus c. I think that's what it is. This is crazy. I don't remember the basic integrals of cosecant squared, but I'm almost certain that's right. If I'm incorrect, please let me know. Yes, trig sub is typically when we use like the x squared minus a squared or the a squared minus x squared or the x squared plus a squared. But some people like to think trig sub is just like I'm using a trig identity and just rewriting it. Okay, here's my next one. And how much time do we got? Yeah, I think maybe we can do one more. Okay, guys, here is this next one. What about integral of natural log 1 plus x? All right, let me know in the comments what you think this is. And I apologize. Okay, hold on. Maybe. I was really hoping that it was maybe the background, but it's not. Okay, anyway, we'll just go back to this. Okay, someone said by parts. How can you use series to make up other series? Man, someone already jumping in on this. I think that's someone might have given the correct answer, but I'm curious what you mean by that. Okay, someone said U-sub. And you know what? I didn't use U-sub when I solved this, but let's go ahead and do the U-sub because it'll make it nice for us. So the way it's going to work, and for the sake, just because I already know that we're going to use integration by parts, someone had mentioned this, we're going to go ahead and not use u, but I'm going to use t. Okay, I'm just going to use, or let's use w. I'm just going to use a different variable. Whoops. Okay, so w is equal to 1 plus x. So then dw is equal to dx. Yo, this blurriness is crazy. So annoying. So now what we have is we have integral of natural log of w times dw. Okay? And the reason why we did this is because now we can go ahead and use integration by parts. Okay? Remember, integration by parts, we pick our u. And in this case, I think the best form or the best value to use our u is the natural log. Because we're going to have natural log of w. And then du is equal to 1 over w dw. And then dv is just the remaining parts, which is just dw. And that means that v is equal to just w. And so now integration by parts tells us ultraviolet voodoo, uv integral v du. And let's just go ahead and put it on the other side over here. So uv, natural log of u, times w, or not natural log of u, natural log of w, minus v du, v du. So integral of v times du. And as you can see, this already simplifies to just 1. So we have w natural log of w minus dw, or I can just put a 1 there so no one gets confused. And now at the very end, this is just w, natural log of w minus w. Someone had already mentioned that. And now remember, w was equal to 1 plus x. So now we just have 1 plus x, natural log of 1 plus x minus 1 plus x plus c. And if you want to simplify that, you can go ahead and do so. I'm not sure if you can, but there it is. Why not use tabular method? You're absolutely right. I mean, technically, there was only one level of this, so maybe we didn't have to use a tabular method. But yes, the tabular method, otherwise known as the tic-tac-toe method, you can definitely use. But typically, I would use it for problems like this, x cubed e to the x. That one, tabular method, is for sure. I mean, that's what you have to use because I don't want to do multiple integration by parts. Okay? But that's the reason why we didn't use the tabular method in the way you call it. Awesome, guys. Just in time. I believe I did all the... No, there's one more. There's one more. Okay, how about one more? And then we'll be done for the day. This is a nice one. A little juicer. And while you guys are thinking about this, don't forget, I do these lives on Wednesdays here on TikTok. Replays are on YouTube. If you want to see another integration practice, I am going live on Instagram every Tuesday or perhaps Friday. And then I do YouTube stuff too. But all the replays go on my YouTube channel, so you guys can go on there. When do I normally go live? Around this time. I'm trying to keep it consistent. So typically this time on TikTok, and then on Tuesdays around this time, but it's on Instagram. Yeah, I did a partial fraction decomposition one, but I'll definitely do some more. I promise. All right, let me know in the comments what y'all think. What do you think, nerds? I think I'm going to start off by first making U-sub. I agree. The U-sub will be extremely helpful here. So let's go ahead and make our U equal to sine x, and du is equal to cosine x dx. Now, why did I choose that? Well, I see a cosine x by itself there. I want to use the sine because I know the derivative of that is going to be cosine, so it's going to cancel out. Because look, if I rewrite this, cosine x dx, that's cosine x dx, that's just our du. So we have du over root 4 minus u squared. What do we think, y'all? What do we think? This is a perfect opportunity for us to do a trig sub. And let me show you how this works. Okay? I personally like to draw my triangle because then we use SOHCAHTOA and all that stuff. I have my theta. And I'm going to make 4 is going to be my hypotenuse, not 4. 2 is going to be my hypotenuse. U is going to be my opposite. And then if you use Pythagorean theorem, you'll see that this is root 4 minus w squared, or 4 minus u squared. Okay? So what that means is we have sine theta, if you follow your SOHCAHTOA, sine theta is equal to opposite over hypotenuse. In other words, 2 sine theta is equal to u. And now we take the derivative of this thing here. So 2 cosine theta d theta is equal to du. Okay. That takes care of our du. We found du. Again, du is equal to 2 cosine theta. But now we need to find out what root 4 minus u squared is. Well, it's sort of here. So what we can do is, I'll kind of put it up here. If you use your trig function, secant theta is equal to adjacent over hypotenuse. That's not secant theta. That's cosine. Cosine theta is equal to adjacent over hypotenuse. So this is root 4 minus u squared over 2. I can move the 2 to the other side. So 2 cosine theta is equal to that root value. So now what we have, okay, so now what we have is we have integral of du, which is this entire thing, 2 cosine theta d theta over root 4 minus u squared, which is 2 cosine theta. 2 cosine theta. Guys, look, cancels out. And so what we're left with is integral of 1 d theta. And at the end, we can just say that this is equal to theta plus c. Now, our answer was in terms of x, so we have to go back. And since we know that sine theta is equal to u over 2, then if we take the arc sine of that, that gives us just theta. So down here, whoops, instead of theta, we now have arc sine of u over 2 plus c. But again, this was in terms of x. So what was our u value? Let's go ahead and scroll down or scroll back up. What was our u value? Our u value was sine. Bruh. So now we have sine inverse of sine x over 2 plus c. Sorry for it going dark there for a second. My dungeon has automatic lights and it goes away. So we have arc sine of sine x over 2. Let's go. I like this problem. I'm so glad that I didn't finish the live without doing this one. Anyway, guys, I'm going to take off. Please feel free to like this video. Follow me here on TikTok. I'm also going live on Instagram where I post other content for you guys to enjoy. And I'm also going to post the replays on YouTube. So please subscribe there and just be on the lookout for this live where you guys can go and review these integrals on your own. Awesome. But anyway, it's always so fun. It's always so fun to be on here. So before okay, it might sound like a no, but can you do anything to cancel out the sine and arc sine? See, I was thinking that, and the only thing you could really do, because this is like sine inverse of sine over 2, I don't think you could do anything. I'm almost tempted. If the 2 wasn't there, I think you could just cancel it out, but because it's divided by 2, I would just leave it. Okay? So you cannot do that. And that's not a dumb question. That's a very valid question, so thank you. But anyway, guys, I'm going to head out. Again, please feel free to like this video, like the live, subscribe to my YouTube channel, follow me on Instagram, follow me here on TikTok. I'm everywhere. But hopefully, I can see you guys next week around this time. And then if you want to catch me on Instagram, I'm going live on Tuesdays around this time as well. Always a fun time with you guys, a bunch of nerds. But I'll see you guys next week. Until then, take it easy. See ya.